Okay, so today we're going to talk about negations of quantified statements. The negation of a statement of the form for all x in D, Q of x, is logically equivalent to a statement of the form there exists an x in D such that not Q of x. So the inverse, the negation of a universal quantifier is a existential quantifier with the predicate negated. Likewise, the existential quantifier negated is the universal quantifier with a negated predicate. So when you flip when you negate, you change the quantifier and negate the predicate. This is the case without respect to the predicates and the domains of the predicate variables. So, what are the negations of the following statements? I think I have this on another side. For all p in primes, p is odd. The negation would be there is a p in primes such that p is even or not odd. The inverse of the negation of the original predicate. So the statement, there exists a triangle T such that the sum of the angles of T equals 200 degrees. Well, the negation of that would be for all triangles T, the sum of the angles of T equals or does not equal 200 degrees. What about the statement, no politicians are honest? No politicians are honest. For all X who are politicians, X is not honest. That's putting it formally. And then in the negation of that, there exists a politician X such that X is honest. So some politicians are honest. Whether you believe that or not is entirely a different story. But the informal negation would be some politicians are honest. Negations of universal conditional statements. If you negate the universal quantifier, you get an existential quantifier with a negated predicate. In this case, the predicate is a conditional, and we know from previous chapters and lessons, the inverse of the predicate of the conditional is if p then q is p of x and not q of x. if you remember that from our section on conditional statements. So to look at this in a more concrete example, this is the formal version of all blondes have blue eyes. All people that are for every person, if that person is blonde, then that person has blue eyes. The negation of that is there exists a person, P, such that P is blonde and P does not have blue eyes. So some blondes have blue eyes. The relationship between the universal quantifier, the existential quantifier, and or. The universal quantifier is equivalent to a series of ands with each element Q of each element in D. It's only true if all the elements in D satisfy the predicate Q of X. Okay? Likewise, the existential quantifier is a series of or statements. There exists an X in D such that Q of X is true, is the equivalent of saying Q of X1 or Q of X2 or ... Q of Xn. For some element in D, there is a element that satisfies and makes Q of X, Q true. When you negate the this one, the existential quantifier, and apply De Morgan's law, you have not Q of X1 and not Q of X2 and ... and not Q of Xn. Because you change the sign and invert the and negate the individual predicates, which is the same as the universal quantifier with negated predicates. It's just applying De Morgan's law to the expanded form of the existential quantifier. So now the vacuous truth of universal statements. Consider the statement that all the balls in a bowl are blue, when there are, in fact, no balls in the bowl. Is the statement true or false? Let's see. It is only false if and only if the negation is true, right? So the negation is there exists a ball in the bowl that is not blue. right? That's a negation of all the balls are blue. The negation would be there's one ball, at least one ball in there that is not blue, right? So that would be the negation. But the only way for the negation to be true is for there to actually be a non-blue ball in the bowl. And there is not. So the negation is false, and the original statement is true by default. So let's see here. You have a you have the for all x and d, all x balls in the bowl. If p, then q. Let's say in general, if p, then q. It is called vacuously true if and only if p is false for every d x in d. So, in the case of the blue balls in the bowl, it would be for all balls in the bowl. If the ball is in the bowl, then the ball is blue. The negation, going back a little bit, would be there exists a ball in the bowl such there is a ball in the bowl and it's not blue. The ball is not blue, which is false because there is no ball in the bowl. So you can see it would be false. The negation of the original statement would be false, making the original statement true. So let's see here. And we also get into, let's see here, variants of universal conditional statements. The contrapositive of the statement, if P then Q, for all X and D, if P then Q, the contrapositive would be if not, for all X and D, if not Q, then not P. And that is equivalent to the original statement. Whereas the converse would be for all X and D, if Q, then Q of X, then P of X, it is not equivalent to the original statement. And the inverse is the contrapositive of the converse. So for all X and D, not P, then not Q, which again is not equivalent to the original statement. Though these two statements are equivalent, the converse and the inverse. So what are the contrapositive and what is the contrapositive of if a real number is greater than 2, then its square is greater than 4? I'm sorry? The contrapositive would be if the square of a real number is less than or equal to 4, then the number is less than or equal to 2. The converse, if the square of a real number is greater than 4, then the number is greater than 2. And finally, the inverse would be if a real number is less than or equal to 2, then the square of the number is less than or equal to 4. Which if you look at these, okay, the original statement, if a real number is greater than 2, then its square is greater than 4. That is true, right? The contrapositive, if the square of a real number is less than or equal to 4, then the number is less than or equal to 2. Right? So that's also true. So they are equivalent. But the converse, if the square of a real number is greater than 4, then the number is greater than 2. Is that true? No, because the minus 3 squared is 9, which is greater than 4, and the number is less than 2. And the inverse, if a real number is less than or equal to 2, then the square of the number is less than or equal to 4. Well, minus 3 again is less than or equal to 2, and the square is greater than or equal to 4. So that one is also not true. So the inverse is not true in that case. All right, necessary and sufficient conditions. Let's get my glasses here. For all x, R of x is a sufficient condition for S of x, means that if R of x, then S of x. So that's a sufficient condition. A necessary condition is the inverse of that, which means that if R of x is a necessary condition for S of x, then for all of x, if not R of x, then not S of x. Or equivalently, the converse, if S of x, then R of x. So necessary condition is the inverse or converse of the original sufficient condition. Only if means that if S of x, or if not S of x, then not R of x. Or equivalently, the original statement, the sufficient condition, if R of x, then S of x. So how about each of these, how about these following statements without using necessary or sufficient? Squareness is a sufficient condition for rectangularity. What's that less formally? If a figure is a square, then it is a rectangle. Make sense? Kinda? Yeah, I see some confusion on the face here. How about being at least 35 years old is a necessary condition for being President of the United States? I'm sorry? No, you have to be 35 years old to be president. You can run for president under age of 35, but you can't serve until you turn 35. The vice president would serve in the interim until you turn 35. Little poli-sci detail for you. But for all persons X, if X is younger than 35, then X cannot be president of the United States. Or if X is president of the United States, then X is at least 35 years old. So now we got statements with multiple quantifiers. How about this? For all X and D, there exists a Y and E such that P of X, Y is true. And then you can have the other way around, where there exists an X and D such that for all Y in E, P of X, Y is true. They are not the same thing. We'll get to that in a little bit. Actions suggested by the quantifiers are performed in the order in which the quantifiers occur. In the first instance here, for every X in D, there is at least one Y in E that satisfies the property P of X, Y. To show that the statement is true, you must show that for every element in D, there is at least one element of E that satisfies the property. Because you do not have to specify the second element until after you choose the first element, you are allowed to have a different second element for each element you choose. The slides go into another example with using Tarski's world to demonstrate this concept, and again, that would be cumbersome to do in class, so I leave it to you to review the slides on Canvas and look at those examples in Tarski's world. I will give a kind of a big example here. In the cafeteria, you have 4 stations: salad, main course, dessert, beverage. In those stations, you have these items. Uta selects the green salad, spaghetti, pie, and milk. Tim, he's kind of hungry, so he gets a fruit salad, fish, pie, cake, and coffee. Yuen gets the spaghetti, fish, pie, and soda. So given those facts, is there an element in an item I such that all students S chooses I? Is there an item that was chosen by every student? Pi. Yes, true. How about there exists a student S such that for every item I, S chose I? What is that less formally? There exists a student S such that for all items I, S chose I. Is there a student that chose every item? Yeah. And it's false because nobody took everything. How about there exists a student S such that all students Z, all stations Z there exists an item I in Z such that S chose I. There's 3 different quantifiers there. There exists a student that chose at least one item from every station. Yeah, it's true. Uda at least chose one from every station. And let's see here, last sample, last question with this chart. For all students S and all stations Z, there exists an item I in Z such that S chose I. For all students S and all stations Z, there exists an item, third quantifier, such that S chose I. Break it down. Every student chose at least one item from every station. Which is true or false? False, because you didn't choose a salad. You didn't choose one from the salad station. All right. Now, translating from informal to formal language. Problems are often presented in informal language. Solving them requires translating them into formal language. So, the following statement. Every non-zero real number has a reciprocal. What would that be formally? I should bring my dry erase markers and have people go to the dry erase and give answers there. But let's see here. I have for all x, element of non-zero real numbers, there exists a y that is a real number such that x times y equals 1. That's putting it formally. And there is a real number with no reciprocal. There exists a real number such that for all other real numbers, x times y does not equal 1. Both statements are true, of course. So, now, translating from informal language into a formal form allows you to prevent ambiguity. You just have to be very careful about translating from informal to the formal form. And let's see here. Negations of statements with more than one quantifier. I think this is the last page of this. For all x and d, there exists a y in E such that P of X, Y is true. Negate that. First, you take care of the negation of the first quantifier, which is to change the quantifier from universal to existential, and then invert what comes after it. Then, since you have another quantifier still being negated, you change the quantifier to the existential quantifier to a universal quantifier, and then invert the predicate. And therefore, you get this form instead of the previous. Instead of the as the negation of the original form. So you can use the same rules to negate statements with several quantifiers that you use to negate simpler quantified statements. So the slides use another Tarski's world example. You can check that out at your leisure in the slides. The order of quantifiers. Consider the following statements. For all persons X, there exists a person Y such that X loves Y. Basically, everybody loves somebody. Okay? And the same predicate, X loves Y, but switch the quantifiers around. There exists a person Y such that all persons X, X loves Y. There's one outstanding person that everybody loves. There exists a Y such that all persons X love Y. There's one person, there's at least one person everybody loves. If there was a person called Bacon, that would be it. But yeah, the order of the quantifiers changes the meaning of the statements greatly. If the quantifiers are of the same type, the meaning of the statement does not change with the order of the quantifiers. Now, this little section here, formal logical notation. In some areas, logical statements are expressed in purely symbolic notation, and I've been trying to stick to that so you're used to it in class. The strict formal notation, using symbols and variables and that sort of thing as opposed to words. The disadvantage of fully formal notation is that because it is complex and somewhat remote from intuitive understanding, when we use it, we may make errors that go unrecognized when we make the translation from informal to formal language. So you have to be careful when you make that translation from informal to formal. Make sure it's perfectly clear. And then the advantage is that operations can be made completely mechanically. You don't have to consider what the meaning of the predicate is, only that it's either negated or not, true or not, that sort of thing. The symbols and quantifiers, variables, predicates, and logical connectives make up what is known as the language of first-order logic. Finally, for the day, we have there's a little section in the slides on a language called Prolog. It is short for programming and logic. It is a fascinating language. I programmed in it using that language many years ago in the early days of personal computers. But it allows you to create relationships between data and that sort of thing to derive new information, gain insights, and that sort of thing. It is a fascinating language. If you were to find a compiler for it and play around with it, more power to you. It is interesting. As I recall, the instructions, if I'm recalling correctly, some of the instructions can go backwards. If the logic doesn't follow, it'll go back and try a different route in the program structure, which is kind of interesting and can be hard to follow. But yeah, check it out. They have a few slides on it on Canvas in chapter 3. Check it out at your leisure. That's as far as I got in the first section for the day, so we'll call it a day here. The test for chapter 3 will be next Thursday. I will push back the due date for the homework to next Thursday before class. So I will get on that this afternoon before I head home. And then we'll move on to chapter 4. So in the meantime, have a good weekend. See you on Tuesday.